Let's take another example. Now, in the previous example, we have calculated the Fourier transform. That means we have used this analysis equation. Now, let's take another example of the synthesis equation. So, we have been given x of omega. Let it be as simple as the del of omega. So, there's an impulse that is present in the Fourier domain. And let's suppose if we need to calculate the inverse of it, that means if you need to calculate what the signal is going to be in the time domain, that means we have to calculate this x of n here. How can we do that? So let's take this example. So this x of n, as given by the formula, we know this x of n is 1 upon 2 pi integration over a period of 2 pi this x of omega is del of omega and e power j omega and d omega. So this is going to be, now we must observe this integration. This integration here, if we analyze this, any signal e power j omega, and if it is getting multiplied with an impulse, we know what is going to happen. We are going to get the same impulse being scaled by the factor of the signal, with the signal being present at n equals to, the omega equals to 0. If any impulse is getting multiplied by a signal, that impulse is going to get scaled by a factor, and that factor is going to be the value of the signal at 0. So here it is going to be the value of e power j omega n at omega equals to 0. So at omega equals to 0, this exponential is going to be 1. So what we are going to get is equals to 1 upon 2 pi. As this is integration is between any limits of 2 pi, I will take it from minus pi to pi. So we are going to get this del of omega d omega, and we know what is this integration. From the definition of this impulse function, this integration is going to be 1. So this is going to be equals to 1 upon 2 pi. That means if we have a signal in the Fourier domain as del of omega, in time domain we are going to get a constant signal that is going to have the amplitude of 1 upon 2 pi. Now let's consider another example with slightly modified version of the signal. So let's consider this another example here. Where I'm considering similar signal. Let this x of omega, instead of having this as del of omega, let it be a shifted version of omega. So let it be omega minus omega naught. So I've considered a shifted version of this impulse signal. So if we try to visualize this signal, this is going to be an impulse that is being located at the location of omega naught. So let this be an impulse that is located at omega naught, and this is what the signal I'm talking about, and we have considered it here. So this signal is this capital X of omega, that is del of omega minus omega naught. Now let's try to calculate the inverse of this Fourier transform. So we need to calculate this x of n. So if we try to do that, let's try to implement this equation, try to use this equation. What we are going to get here is x of n is going to be 1 upon 2 pi over 2 pi del of omega minus omega naught e power, so I'll make some space here, so e power j omega n d omega. So this is going to be equals to 1 upon 2 pi. Now I can make a change of variable again here. So this omega minus omega naught, I am replacing that with, let's suppose, omega dash. If I do that, so omega minus omega naught, if I make it equals to omega dash, what we are going to get is this omega is going to be omega dash plus omega naught. Now if we look at the limits of this omega, small omega, the limits in the interval of 2 pi. Therefore the limits of omega dash is also going to be in the range of 2 pi, just because there is a scalar factor, or there is a shift in the range. You can see that the range of omega dash is going to be again in the range of 2 pi, merely with a shift of omega naught. So just because this range is being shifted, the total range is going to be of 2 pi. So there's going to be no change in the limits of this integral. What we're going to get here is the expression that is going to be equals to 1 upon 2 pi limits over a period of 2 pi del of omega dash e power j. Now this omega is going to be omega dash plus omega naught times n d omega. Again I can take this e power j omega naught n outside this integration. So what we are going to get here is e power j omega naught n by 2 pi times integration over a period of 2 pi del of omega dash, and just because this omega dash e power j omega dash n is a signal again that is going to get multiplied with del of omega, we are going to get del of omega dash itself, just because this is the multiplication of an impulse with a signal, and we know what is that going to be. It is going to get the same impulse being scaled by the value of the signal that is located at omega dash equals to 0. So if we put this omega dash equals to 0 here, we are going to get this signal as del of omega dash. So this is going to be equals to e power j omega naught n by 2 pi. So you can see the change that is incurred here. If we have an impulse del of omega and whose the inverse is 1 upon 2 pi, if we take a shifted version of that same impulse, we are going to get the same x of n, that is 1 upon 2 pi, but the change will be the scaling factor of e power j omega naught n, where this omega naught is the amount by which the signal has been shifted. So there's a close relationship between these two signals. So if we shift the signal in the Fourier domain by an amount of omega naught, the equivalent time domain expression is going to get scaled by the exponential factor of e power j omega naught n, where this omega naught is the amount of shift by which this signal has been shifted in the Fourier domain. Let's try to again take a similar example, a modified version of this. Now similar to this expression here, let's take a shifted version of this impulse and also try to scale this. So if we take, for example, a signal that is x of omega equals to say 2 pi times del of omega minus omega naught. Now we know what is the inverse Fourier transform of del of omega minus omega naught. We have just calculated that. The inverse Fourier transform, that means x of n, for this expression is going to be 1 upon 2 pi times e power j omega naught n. Therefore, if we simply scale this by a factor of 2 pi, so 2 pi will appear everywhere in this equation, and that 2 pi is going to get cancelled with this 2 pi in the denominator. So what we are going to get is x of n is going to be e power j omega naught n. And let's suppose if we take the various shifts of this impulses, so if we take, so if x of omega is equals to 2 pi times del of multiple such shifts, let it be k times omega naught, the x of n in that case is going to be e power multiple such shifts. And of course this k is an integer here, so if we take the impulse being scaled by 2 pi and being shifted by an integer multiple of omega naught, we are going to get x of n that is going to be e power j k omega naught n. Now let's try to again take a modified version of this x of omega. Let's say if x of omega is say 2 pi times again a scalar factor x ak times del of omega minus k times omega naught, the same scaling factor is going to get appeared in x of n. So x of n is going to be ak e power jk omega naught n, where this k is again an integer that is running from minus infinite to infinite. So k may be any integer value. So this k here, as I said, may be any integer value. Now similarly, if we take the x of omega, so similarly if x of omega is equals to, now we are taking multiple such impulses, is 2 pi summation this k running from minus infinite to infinite ak del of omega minus k times omega naught. So what have we done here is we have taken multiple such impulses, we have taken summation of multiple such impulses. So if we do that, this is going to be, so its equivalent x of n is going to be equals to summation k running from minus infinite to infinite ak e power jk omega naught n. And what we have found here is this, the discrete time Fourier series representation. So this expression what we have obtained just now is the expression that we have seen for the discrete time Fourier series. So this expression here is the expression for discrete time Fourier series. So this is discrete time Fourier series representation. and we know this discrete time Fourier representation is meant for Fourier series representation is meant for periodic signals, that is x of n. And these AKs are nothing but the Fourier series coefficients that we can consider. So the scaling factor here, that AK, are the Fourier series coefficients of this AK, of this x of n. So the interpretation is that if we have a signal that is periodic in nature, and if we are aware of its Fourier series coefficients, we can always find out the Fourier transform by simply scaling those Fourier coefficients. So let me write that here. From this observation, let's have a close look at these expressions. Let's quickly go through what we have done so far. We have taken an example of an impulse in the Fourier domain, and we have seen what is going to be its equivalent in the time domain. So x of n here for an impulse was 1 upon 2 pi. If we take a shifted version of such impulse, we are going to get same 1 upon 2 pi, but with a scaling factor of e power j omega naught n, where this omega naught is the shifted amount, or the amount of shift that has been incurred in this del of omega. So if we shift the signal in the Fourier domain, we are going to get a scaling factor of e power j omega n in the time domain. Now we have taken another case where I have taken a scaled version of that shifted impulse. So that is 2 pi times del of omega minus omega naught. So that 2 pi is going to get cancelled, and what we are going to get is e power j omega naught n. Now I have taken multiple such impulse that are located at integer multiple of omega naught. So if we take any integer multiple of omega naught, the shift to be any integer multiple of omega naught, what we are going to get is e power jk omega naught. So only change is going to be in the shift here. Earlier the shift was omega naught, and now the shift is k times omega naught. The shift is going to be k times omega naught here. And similarly, if we take 2 pi times some scaling factor, some scalar, that can be again a complex number, maybe a complex number. So 2 pi times some scalar times del of omega minus k omega naught, that shifted version of the impulse is going to get reflected in the time domain at exponential factor. Again, the scalar, that is ak, is going to be retained here. So we can see the evolution. First we have taken a simple version of this simple impulse. We have seen what is the time domain expression. We have seen the shifted version of the impulse in the Fourier domain. We have seen what is going to be the time domain expression. We have taken now the shifted and the scaled version of the impulse. Shifted and the scaled version of the impulse. We have seen what is going to be the time domain. And if we take multiple such shifted and scaled version of the impulses, we have arrived at the equation what we have seen earlier as discrete time Fourier series. Now this is the Fourier domain pair. This is the, if x of omega is this, the shifted and the scaled version of the impulses, we're going to get x of n, that is going to be discrete time Fourier series expression. So we can interpret this in a reverse way. If we have a signal like x of n that is having the Fourier series coefficients as AKs, that are the scaling factors, then we can calculate x of omega by simply scaling that with 2 pi and multiplying that with impulses that are located at integer multiple of this omega naught, that is the fundamental frequency. So this is a beautiful relationship between the discrete time Fourier series and discrete time Fourier transform. So let me write that. So the interpretation of this is that if we have Fourier series coefficients AKs, we can calculate Fourier transform by multiplying AK with 2 pi and impulses that are located at integer multiple of fundamental frequency, that is omega naught, which is 2 pi by n. Now this can be seen from this expression in red. So the expression here indicates everything what we have written here. So if you have a signal x of n whose Fourier series coefficients are known, that are AK, then we can calculate the Fourier transform x of omega. We just need to take those AKs, scale that with a factor of 2 pi, and impulses that are located at integer multiple of this fundamental frequency, that is omega naught. And this fundamental frequency is the 2 pi by n, that is the signal, the fundamental frequency of x of n, where n is the period by which this x of n repeats. Let's take an example. Say for example x of n is equals to cos two pi by phi n. Now this is the periodic signal and we can calculate its Fourier series coefficients easily. So if Fourier series coefficients are known, so this cos omega naught n, so this omega naught here is 2 pi by 5. So this is the omega naught here. This equation can be written as equals to, we know from Euler equation we can write that as half of e power j 2 pi by 5n plus e power minus j 2 pi by 5n, and this is going to be, of course we can distribute this half factor, so it is going to be e power j 2 pi by 5n plus half times e power minus j 2 pi by 5n, and this half and half are the AKs. So this is a1 and this is a minus 1. This is the Fourier series expression. So the Fourier series coefficients, Fourier series coefficients is a plus minus 1 equals to half. Now from the expression that we have obtained previously here, If we are aware of this ak, we can calculate the x of omega. So we are aware of this ak's. We can calculate the Fourier transform as x of omega equals to 2 pi times this summation ranging over this k, because the other k's are 0, so k is equals to plus minus 1 ak del of omega minus k omega naught, and we know this omega naught is 2 pi by 5. So the expression is going to be x of omega equals to pi times del of omega minus 2 pi by 5 plus pi times del of omega plus 2 pi by 5. So this is the Fourier transform of the signal, the periodic signal, that is cos 2 pi by 5 times n. So that's the beauty of the Fourier transform. We have seen this already for the continuous time case. Now we are looking at the discrete time case. So if we have a periodic signal that is cos 2 pi by 5n, we can still calculate the Fourier transform if we are aware of the Fourier series coefficients. How can we do that? If we know the Fourier series coefficients that are ak's, we simply need to scale them by 2 pi, and with the impulses that are located at integer multiples of the fundamental frequency omega naught. We have done the same and we have obtained this expression. Let's stop here.